It's time to bring you yet another amazing episode. And now, welcome your host.
Now, some of the major issues that is facing the world today includes climate change, human rights issues violation, lack of access to healthcare and education. We also have insecurity issues, corruption, environmental degradation, poverty, and the likes. Now, in spite of the debates and counter debates here and there, it seems that these challenges are not abating. Which way to go? What are we doing wrong, and how can we make it right? Now, these are the questions that are on the minds of the global audience. On the Backstory with Omobola Stephen, we want to focus on what has not worked and what we make it work. We have expert and professionals who share disruptive yet constructive mindship conversations on topics and subjects that are related to government and politics, society and culture, the environment, science and technology, and also the economy. Now, the podcast mic is set, and my name is Omobola Stephen. Welcome to the Backstory with Omobola Stephen. Today, I have Frank Ladd, who is a research associate at the University of Canterbury. He is also the author of the recent book, Just Plain Wrong. Welcome to the Backstory with Omobola Stephen, Frank Ladd.
Yo, hey, Caro, Omobola, fabulous. Yeah, good. Well, yeah.
Thank you for joining me on the show, Frank. I'm loving the energy already, and thanks for your time.
Yes.
Looking forward to this conversation on how we can resolve the touted mysteries of quantum physics.
Good. Yeah.
Yeah, and so you'll be talking also about your recent book, Just Plain Wrong. So I'm really looking forward to a really transformative discussion we're going to have today on the show.
Good.
Sure. So your most recent book, Just Plain Wrong, challenges the findings of 3 Nobel laureates in quantum physics. So why do you think they are flawed?
What do I think it is for? That's
right.
That's okay. So I need to give you a little bit background. I was interested. You were wondering about how things work, because in a physical sense, that's what physics is about. Physics is the study of how things work. And how things work, when you say how things work, well, what do you mean? How things work at our scale, we're talking about feet and inches and miles and hundreds of miles. Well, at the astronomical scale, they're not talking about hundreds or thousands of miles. They're talking about billions of light years, huge distances. And that's at the astrophysical scale. At the physical scale of mechanics, we're talking about things like bowling balls and structures of buildings and carrying weight. But at the quantum scale is the tiny scale of particles of matter, electrons and photons. And the scale we're talking about is photons, for example. The mass of one photon is 10 to the minus 50 power grams. That means 0.000000050 zeros before you get to a 1. Photons are actually stuff. Light is light. Light is stuff. It's stuff. The photon is a packet of energy, and it's a physical stuff. And the photons travel in waves, and they also spin. They can spin to the right or spin to the left. And the light that we see by colors, some are short waves and some are long waves. That varies the color that we see. Well, in the 1930s, the mechanics of bowling balls and structures of materials at our scale, that has been known since the time of Isaac Newton and for more than hundreds of years. But at the quantum scale, the mechanics of quantum phenomena, that was developed only in the 1920s and 1930s. And there are two main differences in this mechanics of quantum phenomena, as opposed to at the scale that we're at, tables and chairs, that we call the classical scale. At the classical scale, if you roll a bowling ball down a bowling alley and you roll it at this angle, accelerating at this rate and spinning at this velocity, with the coefficient of friction of the floor such and such, the laws of physics will tell you what happens. You get a strike or a 6-10 split, or the only reason we don't know what will happen is because we don't know exactly what is the acceleration of your ball, what is the angle, what is the spin. Okay, so that's one feature of quantum mechanics, but quantum mechanics would tell you what classical mechanics would tell you what happens. But at the quantum scale, if you send a photon down a tunnel and it comes to a polarizer, like you're polarizing sunglasses, some light goes through and some goes through. Why does some go through and some not go through? That's the study of quantum mechanics. And quantum mechanics don't tell you whether the photon will go through or not. They just tell you the probability that it will go through. That's one feature by which quantum mechanics differs from mechanics. They only tell you probabilities. Well, the other feature of quantum mechanics is that's different is that when you roll a bowling ball, you go in a bowling alley and there are 25 lanes on one side and 25 lanes on the other side. Well, when you apply the laws of quantum mechanics to your bowling ball, you don't have to pay any attention to the bowling balls on the other side of the room, other side of the hall, because quantum mechanics are local. What's going on at your pins, that's your local. But with respect to light, well, Einstein had thought the behavior of light was also local, but the defiance of Bell's inequality apparently is challenging that. So that's what happened. So what happened in the 1930s is Einstein was one who was very concerned about these probabilities. What are these probabilities? The mainstream view of quantum mechanics is that the probabilities are in the photons. Probabilistic behavior are in electrons. There's probabilities in nature. And what they thought is that we have discovered in quantum mechanics that nature at small scales is random. And at the scale of you and me, because of the laws of large numbers, many of these ones, that's why things are solid at our scale. Well, Einstein was very concerned about these probabilities. He said, what are these probabilities? Probabilities cannot be in the photons, in the electrons, because his famous saying was, I cannot believe that God rolls dice. That is, that nature is the outcome of something random. He said there aren't any probabilities. Probabilities represent our uncertainty about other things that are going on at quantum scale that we don't know about. But Einstein was shouted down. In the late 1930s, Niels Bohr and what is called the Copenhagen School of Quantum Mechanics specified this, that we've discovered that nature is random. And Einstein, by the end of his life, he was considered to be sort of a nutter because he could not accept that nature is random. Well, how about John Bell? Bell's inequality. John Bell, he was a young physicist in the 1960s from Ireland. He was working in particle physics. He worked at CERN, the European Center for Nuclear Research. He worked there, and he was interested in reinstating Einstein's views, but he came upon a problem. When he found a certain example of behavior of electrons and photons where in the probabilities of quantum mechanics, if Einstein were right about the locality of quantum mechanics, then the probabilities of quantum physics defy what's come to be called Bell's inequality. It's equality. Certain probabilities have to be bigger than other probabilities. That's what Bell's inequality says. So he made this inequality, and what happened is that if Einstein's principle of locality is true, then the inequalities are defied. So the conclusion of quantum physics is that the behavior of quantum materials are not local. What's going on in your light bulb has something to do with what's going on in my light bulb, and we're so far away from each other, but that's what they think. Well, Bell's inequality was thought to be defied, and by 10 years later, there was a French young physicist in 1980s, Alain Aspect, and he said, oh, I should say one thing about Bell's inequality. Bell's inequality, it pertains to what they call a Gedanken experiment, a thought experiment. It's an experiment that you cannot actually do this experiment, but you can think about it. Here's the experiment that they talk about. Suppose, when you and I get hit by light, we're getting hit by billions and billions of photons, more than billions. but we can make intense light, or we can make very, very faint light. And actually, we can make light so fine that we can generate 2 photons, not billions of photons, 2 photons. And what we do is we send the 2 photons down a tunnel, 1 kilometer long, and at the end of this, in opposite directions, one comes to station A, one comes to station B. And at the end of these tunnels, these photons meet polarizers, polarizing material just like your sunglasses. And the physical structure of the polarizing material is that in the molecular structure of polarizing material, there are lines. There are lines in the structure. And if you have a lines, if you set the line this way, and the photon is coming at the same rotational angle as the lines of the polarizer, it'll pass right through. But if you turn the polarizer 90 degrees, it won't pass through. And if you put some angle in between 0 and 90 degrees, it might pass through and might not pass through. And quantum mechanics tells you those probabilities. So here's the experiment. This is what Bell's inequality is about. We're now going to send 2 photons, and we're going to send them in opposite directions down a tunnel 1 kilometer long to polarizer. And at the polarizer at station A, you can set the direction of your polarizer at direction A or A prime. And at B, you can then set that polarizer at direction B or B prime. Okay, so, well, what happens, this whole experiment that we're talking about, it takes place in 1 nanosecond. That's 10 to the minus 9th seconds, 0.00001 seconds. That's how long this is going to take. And what will happen in this very short time interval is that it will be determined, are we going to send the photons to stay to direction A and B, or A prime and B, or A prime and B prime, or A prime and B? Those are the 4 possibilities. So they shoot off the photons, set the directions of the polarizer, and when the photons get to the end, the photons are either going to pass through their polarizers or they're going to be blocked. So we're going to and the way we tell whether they pass through is we put a photographic plate behind the polarizer, and if the photon gets blocked, nothing will happen on the photographic plate. But if it goes through, it'll make a mark. Light touches the plate, and we get a picture of this photon coming into the plate. Okay, so at the end of the experiment, we're going to find out, we find out the direction that we send the photons, AB or AB prime, and we also find out, did the photons pass through or not? Yes, 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 no, no, yes, no, no. And quantum mechanics, the mathematics of quantum mechanics, specifies the probability for yes, 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 no, no, yes, no, no, as a function of the 2 directions. Did they go through at AB? Then we'll have 4 probabilities. Did they go through at AB prime? Then we'll have 4 probabilities. If we set it at A, the Bell's inequality does seem to be defied by the mathematical probabilities, and that's why the physicists reject the principle of local realism when it pertains to quantum behavior. Well, there was a guy in the 1980s, then Alain Aspect. He comes along and he says, wait, this great result of quantum mechanics, isn't this based, can't we observe anything about it? You mean it's just a thought experiment? Aren't we doing physics here? We're not talking about dreams, we're talking about physics. So he said, I'm going to make some experiments that we're going to find out whether Bell's inequality is defied or not. And he made up his experiments, and he found out, oh, the inequality, yes, is defied, and physics is local. Quantum physics is local.
What do you think are some unsolved mysteries of quantum physics?
Well, the mysteries, my view is that there aren't any mysteries, because this defiance of Bell's inequality, it's based on a mistake. There's a mathematical mistake, and my book explains what the mathematical mistake is about. We could go into that, exactly what the mistake is if you want to, but it's based on a mistake. And so that's my challenge to the physics and mathematical physics community. Can't you see there's a mistake here? Bell's inequality is not defied, and quantum mechanics is local. Quantum mechanics, your light bulb has nothing to do with my light bulb, or it has nothing to do with the star that's so many billions of light years away from you. Well, they think it does. So As far as I'm concerned, there are no mysteries. Thinking that there are mysteries is based on a mistake, and it's a mistaken understanding of how these probabilities work and what they mean. And that's what my book is about. My book it is about a mathematical mistake, but it's written in such a way. It's written completely technically. It's written for mathematicians and physicists to rethink this. But I also wrote it for a generally educated reader who might be interested by this. Many people are interested in foundations of science, and there are many books about issues of this sort. So my book is written for a generally educated reader who's not frightened by mathematics. You might not understand every equation that's in the book. The book is not all equations. It's a description of what these issues are, and the issues relate to mathematical things. But that's what the book is about, and it's meant to be enjoyed by any educated person who's interested in foundations of science.
Now, the currently accepted understanding of the physical mechanics of matter at very small scales is seriously mistaken. The question on the minds of the audience is, why is this so, and what is the locality principle?
The locality principle is that what's going on at the one polarizer with the one photon has nothing to do with what's going on at the other photon. Well, why this is thought to be is that, and what is a mistaken understanding of what these probabilities are about. It turns out that when you ask for the probability of, do the photons go through? Yes, 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 no, no, yes, no, no. Well, the quantum probabilities are the same value for yes, no, and they are for no, yes. And that's a signal that we have a symmetric distribution. There's like the symmetry of your face. The one side looks like the other side. Well, the symmetry of the experiment is when all we know is that light is coming down to some angled polarizer down there, and over here there's light coming to some angled polarizer. They look the same to us, and that's why those probabilities are the same. Well, the quantum physics people, they think the fact that the probability for the photon going through at station A has something to do with the direction at station B comes because they don't really understand what the symmetry of this distribution is about. So the funny thing is, the probability for yes, 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 no, no, yes, no, no, it depends on both the direction at A and at B. And what Einstein's concerned about, he called this spooky action at a distance. And what happens when the photon, when it takes off, when the two photons take off, they don't know if they're going to A or A prime and B or B prime. But the probability for their behavior depends on both A, B, A prime, B, A prime, B prime, A prime, B. So it depends. So Einstein's concern was this: suppose this photon is traveling along, it comes to its polarizer, and it finds out, I'm coming in at A, not at A prime. I'm coming in at A. And its behavior depends also on what is the angle direction at B. Is it B or B prime? And the question is, how could the photon at A know whether the one at B is coming in at B or B prime? Because they didn't know when they left. They're traveling at the speed of light. The speed of light is 186,000 miles per second. That's how fast light goes. So how could it know whether this one is coming in at B or B prime? Because when the photon comes in at B or B prime, suppose it finds out it's coming in at B prime, there's no way that it can send a signal over to this other photon to say, oh, I'm coming in at B prime, not B. Because if he were going to, it would have to send a message faster than the speed of light to get over there to tell him I'm going, or her, I'm going in at B, not B prime. So that's what's considered the mystery of quantum mechanics. But the point of Einstein is that those probabilities are not in the photons. The probabilities represent our uncertainty about, at this tiny, tiny scale, there are other things that are going on that we don't know what they are. His argument was quantum mechanics, the theory of quantum mechanics must be incomplete. There must be some other things that we don't know about yet. that we should investigate. And it's hard to investigate at tiny, tiny, tiny scales, but some people are still trying, but some people have given up. Some people say, no, we have understood that nature at the small scale is random. It's based on probabilities. It might be doing this, might be doing that. And my view is that it's not random. The probabilities are uncertainty in our minds. They're not properties of the photons. That's what the issues are about. And the physics people don't want to hear about this because they have already settled their mind. They're not interested. I just went to a meeting of the American Physical Society, and the people who do the quantum physics and study Bell's inequality, no, they didn't want to hear what I have to say. But the book is out there and people can read it, and it's true. They've made a mistake, and they'll find out in time. Yeah, that's my view.
All right, thanks for sharing your insight, Frank.
Yeah,
Now,
good.
what do you think, or do you think quantum phenomena can drive technological advancement, especially in this 21st century?
Oh yes, well, definitely. That's one of the issues. My book has nothing to do in detail with the computational coding of quantum computers. But you've probably heard of quantum computers and quantum information processing. What that is about is that your computer that you're working on now, that's based on electricity. We send electronic signals to gates, and the gate can be open or closed. So we code that as a 1 or a 0, and the basic information the basic information transfer of regular computers is based on sequences of ones and zeros. 1 0 0 1 0 1 0 0 1 0 1 1 1. That's a code that tells you what information that you want to be sending. Well, but that's based on electricity. Well, the speed of electricity the speed of electrons is much slower than the speed of light. Light is going at something like, well, it's 186,000 miles per second. The speed of an electron is much, much slower. It's like 100 or 200 times slower than that. And electron speed, it depends just how the electrons are being processed. But that is nowhere near the speed of light. So the idea of quantum mechanics as a way of sending signals that are based on these probabilities, well, if you send a lot of signals at tiny, tiny probabilities, then you can send information much, much faster than electricity can. So that's the hope of quantum technology applied to computational systems. And people are at this physics meeting. There's people that are working on all sorts of this stuff, and it's happening. It's happening slowly. Well, my view is that I think they're getting bogged down in some types of problems that are not really problems because they've made this basic mistake, thinking that the quantum mechanics are not local. Well, they are local, and it's our uncertainties there. So my book is not about coding of quantum computers, but that is the application of quantum mechanics to information processing. That's currently quite a hot topic in physics and material technology.
Now, I'm thinking in my head, do you think quantum physics or mechanics has already changed the world?
It has changed the world. There are mechanics that are involved in quantum probabilistic signals that are sent. Yeah.
All right, so good. Do you have any important projects or any information you think is going to be beneficial, is going to add value to the audience of the backstory? You can share them if you have any.
That's okay. So my own bigger interest in research is in what we call the subjective theory of probability. Probability has been a controversial subject for hundreds of years. From the time of Galileo, he was also interested, but by 17th, 18th, 19th century, there has always been a division in the way people understand probabilities. What do you mean when, suppose I said that my probability for my bicycle having a flat tire this year is 0.03. The question is not is it 0.03 or 0.04, but what do you mean when you say something like that? Well, there are two views of probability. One's called the objective view of probability. One's called the subjective view of probability. The objective view says that nature is random. That's the point of view of these the quantum theorists now. Nature is random. Things happen by chance. There's some probability that it will rain today at your town. There's some probability my bicycle will have a flat tire. They think there is a probability, and the statisticians who think this way, they try to estimate probabilities. Well, my point of view, the subjective point of view, there have been many people in the 20th century who've been developing this, but the most famous one was named Bruno De Finetti. He was an Italian probabilist, 1906 to 1986, and he's famous for his one short saying, "Probability does not exist." Don't go looking for probability out there. Look for it in here. Probability is a measure of your uncertainty. Let's take a question like this. What an objectivist would ask the question, what is the probability that Frank's bike will have a flat tire this year, between now and 1 year from now? Well, the thing is, we're never going to observe that probability. There isn't any probability. We're going to observe I have a flat tire or I don't. So what is the probability? There isn't a probability, but you don't know what kind of a bike I ride. You don't know how often I ride a bike, where I ride it. I know all those things. You don't know whether I'll have a flat tire, neither do I. But I know how old my bike is. I know how bald the tires are. I know how often I pay attention to the tire pressure. You don't know any of that, but you don't know whether I'll have a flat tire, and neither do I. But our uncertain knowledge is different. What's your uncertain knowledge about my bike? Well, you look at Frank, he's sitting in a hotel room in San Francisco. He got a nice white shirt on him. He got nice glasses. I'm not going to, you might think, well, he's not going to be riding a junker. He's not going to be riding a bike falling apart with bald tires. Well, that's all that you know about my bike. And then you see I'm apparently an agile person. I'm a bike rider. I can tell you that I do ride a bike regularly. I don't have a car. I ride bike. Okay, Christchurch is a flat city. We're flat, so it's easy to ride bikes. It's not like San Francisco. Anyhow, but your knowledge about my bike is different from my knowledge. You're uncertain about whether I'll have a flat tire, so am I. So our probabilities are measured by, how do you measure your probability? You think here's a ticket, Omobola. I would say this ticket is worth $100 if Frank's bicycle has a flat tire this year. And if it doesn't have a flat tire, it's worth nothing. Okay, so here's the ticket. You can have it. You can have it if you pay for it. Here's the question. Would you rather have $1 or would you rather have this ticket? The ticket might be worth $100, might be worth nothing. Well, $1, you might say, well, I'll take the ticket. Maybe I'll get $100. And if I didn't get that $1, that's not so much. Well, how about $99? Would you rather have $99 or this ticket? It might be worth $100, might be worth nothing. And you'd say, oh, I'll take the $99. How about $80? I'll take the $80. How about $2? I'll take the ticket. How about $60? I'll take the $60. How about $3? I'll take the ticket. How about $10? Get to $10, down to 10, up to 10. You might say $10. I don't care if you give me $10 or give me that ticket. The ticket might be worth $100, but it might be worth $0. But you could have $10 for sure. You might come to $10. 10 out of 100, 1/10 is your probability. My ticket, I know more about mine. I know different things about my bike you don't know. I might say, well, I'll settle on $2. $2, I don't care if I have the ticket or the probability. My probability is 0.02. Your probability is 0.1. See, we each have our own probability, and probability, we're actually, Omobola, we are uncertain about everything. The only thing we're certain about right now is I'm looking at a screen. I see your face on the screen. You see we're both wearing glasses. You have long hair. I almost have no hair. We're certain of this. But how about my brother Tom? Is he alive? Well, he was 2 days ago. I talked to him on the phone. Is he alive now? He might be alive, he might not be alive. I have a probability for that.
That's your thought with my audience, Frank. Can you share your social media handles and your website so we can connect and learn more about your book and
Sure.
also all the other resources that you have?
Yes, sure. I'd be happy to. There's about the book, and there is a website that's called ResearchGate, ResearchGate, and ResearchGate is a site that almost all of the academic people who do academic research and publication have a page on ResearchGate. If you go to ResearchGate, you will find Frank Ladd, L-A-D, and then you'll see all the publications that I've written. I've written some deeply technical mathematical things, but I've also written some basic statistics for people. Everybody takes a statistics course in college. Well, from my point of view, they learn the wrong thing. One of my papers that people might like to read is why do whales strand when they do? I don't know if you live near the ocean, but I live near the ocean, and on New Zealand beaches, whale strandings are very impressive. You might see 400 whales come up to the shore, and they just stay there. The tide goes out, and then they're stuck. They can't go out. There are certain places where they strand, certain places where they never strand. Well, why do they strand when they do? In that story, in that paper, that was a paper that I wrote for a summer statistics course for adults in Italy. And so
Frank, can you share your social media handles so we can connect?
My social media, I do have I am a space case. I'm an old guy.
All right. Okay. All right. So we can connect with you. Definitely, we can connect with you and learn more about your projects on ResearchGate, as you just highlighted. Is that okay?
And Facebook. I do have a Facebook address.
Okay. What's your Facebook address?
I'm not even sure.
All right. Okay.
You just ask for Frank Ladd.
Connect to Frank Ladd. Is that okay on Facebook?
Connect to Frank Ladd on Facebook. If somebody from one of your listeners wrote me and said, I know Omobola, if they wrote me, I'd say, sure, I'll accept you as my friend, and we'll talk about whatever you want to talk about. Hey.
All right. Thank you so much, Frank Ladd. Thanks for sharing your thoughts on today's show. Yes, especially as we talked about how we can resolve the touted mysteries of quantum physics or mechanics. Thanks for sharing your expertise, your professional insight on this topic of discussion. We really appreciate your time and your valuable contribution.
We have talked for so long. Now I will have to say Ekasu.
I really appreciate it indeed. From the bottom of my heart, on behalf of the audience of the Backstory, we sincerely want to wish you best of luck in your book project, which is titled Just Played Wrong, and in other projects that you will embark upon in the nearest future, Frank. Now, if you'd like to catch up with any missed episodes of the Backstory with Omobola Stephen, you can do so on any podcast distribution platforms or any podcast promotion platforms you bump into online. Just search for the Backstory with Omobola Stephen, and there you go. You have a great time. Listen to professionals share insight on topics, the subjects that are ranging from government and politics topics, science and technologies, the society and culture, the environment, and also the economy. Till I come your way, I need you to stay safe always. My name is Omobola Stephen once again. Thank you.
Just Plain Wrong on Amazon. If you click on the Kindle version, there will be a little box. It says read more. If you click on that box, then there will be a couple page preface to the book and the chapter summaries. Those anyone can read. There are no equations in them. They will tell it just what the story is about. And the printed version, it just goes right to the title page and the table of contents. That's also fine. But if you go on the Kindle version, you'll see the preface and chapter summaries. Omobola, very nice to talk with you.
Nice talking to you also. It was a great show.
If you enjoyed today's episode, make sure you subscribe and leave us a review.